Section: Introduction. In this section, we explored how to improve the pre-training datasets for large language models, LLMs, like DOLMA. These datasets have grown to trillions of tokens and typically consist of two main types of data sources. The first type includes large amounts of web-scraped data from Common Crawl, CC, dumps, which are massive but less information dense and not as filtered. The second type consists of smaller datasets from specific domains or high-quality sources, which are more carefully processed and rich in information but less diverse. One of the main challenges in pre-training LLMs is deciding how to mix datasets from CC and smaller domain-specific sources effectively. Some previous studies focused solely on CC data, while others tried to balance between CC and domain-specific datasets using different methods. However, most recent large-scale language models do not provide detailed information about their pre-training data. There have been attempts to optimize data mix proportions algorithmically at smaller scales, but these methods have not been widely validated for training modern language models. Our goal in this work was to explore a new approach to conducting pre-training data experiments on a reasonable scale. Instead of experimenting with data mixes at the beginning, we adjusted the data mixture at the end of training after achieving meaningful progress on challenging benchmarks. This strategy proved to be effective in improving LLM pre-training data mixes at a fraction of the cost of full training runs. We started with a baseline mix of publicly available datasets that matched the performance scaling of the Llama 2 model family for a 7 billion model trained on 1 trillion tokens. By introducing domain upsampling, where we increased the presence of domain-specific datasets relative to Common Crawl at the end of training, we were able to enhance performance on difficult metrics significantly. This approach led to improvements of up to 6.90 percentage points on MMLU, 8.26 percentage points on GSM-8K, and 6.17 percentage points on human eval compared to the base data mix. Our results made our performance comparable to Llama 2, 7B, but with approximately half the training flops. We also investigated the optimal percentage of training that should utilize domain upsampling, finding that 10% to 20% struck a good balance between general language modeling abilities and targeted benchmarks. Domain upsampling proved to be a cost-effective method for understanding how individual datasets influence model capabilities. By selectively removing math-heavy pre-training data from the upsampled datasets at the end of training, we could quantify the impact of these datasets on specific benchmarks. Section Summary. In this section, we discuss the challenges of mixing datasets for large language models, LLMs, from web-scraped data and domain-specific sources. Previous works have struggled to find the optimal balance between these datasets, with limited disclosure of pre-training data contents in recent models. Our approach introduces domain upsampling at the end of training, showing significant improvements in challenging metrics like MMLU, GSM-8K, and human eval, making our model comparable to Llama 2 but with half the training flops. By adjusting the percentage of domain upsampling during training, we demonstrate an efficient way to enhance model capabilities and evaluate the impact of individual datasets on specific benchmarks. Section: Results. In this section, we will discuss the experiments we conducted to show how domain upsampling can enhance performance and help us understand the impact of different datasets on challenging metrics. Our baseline data mix achieved Llama 2 scaling. To create this mix, we categorized publicly available datasets into 4 groups: large-scale Common Crawl, small-scale Common Crawl, domain-specific data, and code data. We decided on the proportions for mixing these datasets based on how many epochs each group would be seen during the 1 trillion token training period. We allocated 0.5 epochs for small-scale Common Crawl and domain-specific data, 1 epoch for code, and the rest of the tokens were from large-scale Common Crawl. The reasoning behind these proportions was to ensure high-quality data representation within our budget and to emphasize coding ability. Our initial pre-training data mix performance was evaluated for 2 models trained with 0.5T and 1T tokens. The results showed that our models aligned with or performed better than the Llama 2 scaling line on various metrics. Interestingly, the model trained with 1T tokens outperformed the 2T token Llama 2.7b model on certain metrics, indicating better mathematical and programming abilities despite being trained for fewer tokens. We then introduced domain upsampling for the last 20% of training in our 1T token run. This involved adjusting the mixing proportions of our data mix to focus more on domain-specific and code subsets while excluding large-scale common crawl. The results of this intervention showed a significant improvement in model performance on challenging benchmarks without compromising general language modeling capabilities. This enhancement was particularly notable in math and code-related metrics, with scores approximately 10 pp higher than Llama 2.7b. Overall, domain upsampling proved to be an effective strategy for improving model performance, especially on challenging benchmarks. Even with simple heuristics for selecting new data mix proportions, we observed positive effects, indicating potential for further enhancement with more refined mixing proportions. Section Summary. In this section, we demonstrate the effectiveness of domain upsampling in enhancing model performance and understanding dataset impacts on challenging metrics. By adjusting the mixing proportions of our pre-training data mix towards domain-specific and code subsets at the end of training, we significantly improve model performance on benchmarks like GSM-8K and Human Eval, surpassing the Llama 2 model despite being trained for half the tokens. This intervention not only enhances mathematical and programming abilities but also boosts overall model performance without compromising language modeling capabilities, showcasing the potential of domain upsampling as a valuable pre-training data strategy. Section. Changing the duration of domain upsampling enables us to navigate the trade-off between targeting specific domains and general-purpose language models. In this section, we explored how adjusting the duration of domain upsampling can help us balance between focusing on specific domains and enhancing general language models. We questioned whether the improvements seen from domain upsampling towards the end of training were due to the intervention itself or simply because of better data mix proportions overall. By conducting experiments with domain upsampling at different points during training, 5%, 10%, 20%, and 30%, we found that while benchmarks related to math and programming continued to improve with increased domain upsampling, other benchmarks reached their peak performance at around 20% or even earlier. This suggests that pushing domain upsampling beyond 20% could lead to better performance in specific areas like math and coding but at the expense of general language modeling abilities. We also investigated the impact of specific subsets of data, particularly those related to math, on model performance. By comparing models trained with and without math-related datasets during domain upsampling, we found that these datasets significantly contributed to the model's mathematical knowledge and reasoning skills. Removing these datasets led to a decrease in performance compared to the baseline model without domain upsampling. Our findings highlight the effectiveness of domain upsampling in helping us understand the trade-off between targeted domains and general language modeling capabilities in a cost-efficient manner. By using domain upsampling, we were able to measure the impact of different datasets on model performance without the need for extensive training runs. This method provides researchers with a practical way to experiment with pre-training datasets and optimize model performance effectively.